I decided that since I have videos challenging standard cosmology on, excuse me, on the sun and the moon, that I should do one on the Earth. But I don't think this will be too long. I hope not. But what I want to do is I found this, just a randomly selected Earth curve calculator and plugged in some numbers. 6-foot eye height is very common from what people usually use for, a person standing and looking out to the horizon. And I give it a target distance of 7 miles just because when I push calculate it came out with hidden amount of feet, 10 feet, enough that you could see at, some reasonable distance. Because if it's just inches, it doesn't matter. I mean, you can quibble about whether it should be seen or not. And of course, there's no consideration for atmospheric conditions or perspective. But the problem is this drawing that they used that tells you how they made the calculation. And, the calculator presumes all these things. One thing it presumes is that the horizon is the tangent point. The calculations are worthless without that. So H0 is the observer at 6 feet eye height above the ground. The horizon is about 3 miles away, and the target is on the other side of that tangent point, and it's 10 feet high, and they're trying to calculate, distance to horizon, which is the vanishing point, which is the point at which everything is obstructed. So the problem is, when you think about this is not real life. You don't stand over here. You see these angles that these arrows are at? That's perpendicular or a right angle to the surface, wherever the surface is. It's arcing, okay? So if you got right angle here and a right angle here, they're pointing away from each other, right? But the problem is that's not real life. You don't stand, if you're standing upright, this works here, but you're not, when you look at the horizon, you're not looking down at your feet. You see this angle between, I hope you're seeing my arrow. I don't know. Let me know if you're not. But this line, which is pointing from the center of the circle to the edge, which is the radius, and then, 6 feet above that, that angle to the tangent angle is an acute angle. It's less than 90 degrees. When you look at the horizon, you are not looking less than 90 degrees. You're looking at 90 degrees. Okay, if you're just standing straight up and looking straight ahead, that's a 90-degree angle. Okay, so why are they showing you less than a 90-degree angle so that you hit the horizon here? Because what they did was basically reverse engineer, or in statistics, we call that drawing the target after the shots have been fired. They said, well, we can only see 3 miles from a 6-foot eye height. Things start to disappear after 3 miles. That doesn't mean they completely disappear. It means they start going over the edge. If this is a boat going along here and the top of the boat, the boat has some height to it, it'll take some time before that height reaches a point where you don't see it anymore. So this is their 10 feet or whatever it was, 10 and a half feet. And this is the 6-foot eye height. Okay, so they just drew a tangent line from 3 miles to the 6 feet, and then continued the tangent line and decided where this is going to wind up. And this all makes mathematical sense, but not real life sense. Because like I said, if you're perpendicular to the surface of the Earth, you're looking 90 degrees, you're going up like this. You're not looking down here. So again, here is this calculator, and I have the link in the description. I'm pretty sure I put it there. I entered H0, the eye height is 6 feet, and the target distance of D0 is 7 miles. And hit calculate, and it said horizon distance is 2.99. That's 3 miles. It's 3 nautical miles or thereabouts. It's not that precise, but that's generally you're going to be in the 3 mile range. And H1 is the target hidden height. Okay, that's 10.67 feet. So that's H1. Now, I'm going to look at my little drawing I've been working on today. in reality, here is a person standing. They're standing. Here's the radius line from the center of the Earth to the surface, 6 feet up. There's your eye height. This is H0. See the H0 down here? And again, let me know if you're not seeing my arrow. Here's the H0 down here. Here's H0 in real life. Okay, you're looking straight out. Here's a boat. Granted, that's a tiny boat. Let's decide it's an RC boat or something like that. And you're looking straight out. You're in parallel with this tangent line, which if you see this little box here, that indicates a right angle. Okay, so all of these are parallel lines, and if the Earth is curving down and away from you, and you eventually get to your H1 point, the 10 feet, that's at your feet, not your eyeballs, because you are the tangent point. You see down below, they got horizon as the tangent point. No, that is not the tangent point. The tangent point is not the horizon. The tangent point is where you're standing, because that's where the right angle is. You're not looking down here. You're not looking at the base of this. You're looking straight out while standing on the top of a ball, and the ball is falling away from you in every direction. And the ship, if it's going away from you about 3 miles or so, it's going to disappear. I just drew a tiny one. I didn't draw a dot. What would be the point? But the point is that about halfway, a little bit less than halfway to that 7 miles, which again is calculated on an arc, so it's a little longer, a straight line, 7 miles. But the thing is, if the boat were disappearing because of curvature, no amount of zooming or telescope or magnification of any sort would bring it back. It can't, because you've got an obstruction. See, if you go back down to their example, if you're standing here and for some reason not looking straight out, you're looking down a little bit so that the horizon works out to 3 miles, which happens to be the vanishing point, but they made it the horizon tangent point. This obstruction is here. You have the water coming up to meet the object, which is what you see, but then it goes back down again. But the problem is, again, that we are here, not here. And we're looking straight parallel with the tangent, not, with us at the tangent point, not down at our feet so that the tangent works out the way they have it. So curve calculators are all based upon an incorrect placement of the observer and an incorrect eye angle of the observer. It has to be that way, so they work out that why things disappear at 3 miles at a 6-foot eye height, or why that's not necessarily where they disappear, but the height at which the horizon is, or the distance of the horizon, sorry. So, and scale really doesn't matter here. The point is that by their calculator, it is based upon the observer being back over here instead of at the horizon, which is the tangent point. So that's why I have up here, this is tangent, here's my tangent line. And I don't know why I still got that line there. It doesn't belong, but that was just a guideline. Here's the tangent line. It touches the top of the circle where we're standing, because that's where we're always standing, at a right angle. We're in line with the radius, and so we're looking out at a right angle. There's our right angle tangent line. That's how it's defined. And we're just a little above that, but parallel to the tangent line. And we're not looking down at our feet. We're looking really what amounts to straight out into space, looking higher and higher elevation, because if it's an orthographic view and you're not doing perspective, that's where you would be looking. And things disappear not because they, are being hidden by the Earth as they are here, but because they're falling down away from you. But that's not what we see. We see this gray cone here. Like if this is the boat and it's shrinking and shrinking, the water seems to always, it's obviously always going to touch the bottom of the boat, right? So it must be going up, and that's a standard perspective view. And I showed a perspective grid in one of my previous videos on the sun. And we all know, I don't even need to get you a picture of looking down a long hallway. The floor comes up, the ceiling comes down, and the walls come in. So we're looking at that from the side. We're looking at the person's shrinking view of the hallway, you know, so to speak, as we're looking at the side of it, as if we're the fourth wall of the stage. This person is seeing a smaller and smaller boat, but it's staying in the center. It's not going down like that. You know, it stays at your eye height if you're on a flat surface and you're looking 90 degrees, which is normal. So the problem with curvature calculators, as down here, is that they have misplaced the horizon. The observer should be over here, not back here, because, like I said, this is, although you're still perpendicular to the surface, you're looking straight out, and so your line is going up like that on their model. So these calculations don't work. Like I said, all they did was force fit the starting point to be where things disappear, and said, well, must have a certain diameter Earth or certain radius Earth in order to make everything else happen. So, and it works as long as you presume that you're over here and the horizon is just, you know, the 3 mile distance or whatever, depending on your height above the horizon, it's going to get longer, but it doesn't solve the problem. Like I said, scale doesn't matter. The problem is you are at the tangent point. Wherever you are, it's the tangent point. And wherever you look, you're looking parallel to that tangent point, and things come up, you know, the ocean comes up or whatever you're looking out toward. The sky comes down, and this object, the boat, is shrinking. And usually you'll see more shrinkage in the vertical than the horizontal, depending on the conditions, but that's usually because air layers are horizontal, essentially. So you're going to get distortion, but as I went over in my previous video, but the thing is that this is just to show why Earth curve calculators are not accurate, because they arbitrarily chose the horizon as the tangent point when that is not reality whatsoever. You are the tangent point. And then the question is, why do things disappear? It cannot be obstruction of the Earth, because the Earth is falling down away. It's doing the opposite of obstructing. So when people say, where is this hump of water? They're looking at the bottom thing and going, why don't I see that? It must be flat. But the thing is, that's not the issue. The issue is they've misplaced the observer. It's supposed to be in the middle here. And that's all I did with this drawing here. I put the observer on the tangent point where they belong, looked straight out, showed that, you know, of the 7 miles, 3 is just a little short of half of that. That's where things disappear. And it cannot be, because the Earth is curved away that much. So regardless of what anybody might see from other angles, because I had been saying in chats that a person, as our perspective, not perspective, but our viewpoint here looking at the side, we would still see the boat because our distance to the boat never changes. But the observer on the screen there, this person here, they're dealing with distance going away from them. And so it gets smaller and smaller and disappears. So all I tried to do was line up their H0 with, you know, mine. I even tried to use the same colors, their H1 with mine. And the heights, you know, this is 6 feet above, and this is 10 feet above, and when it's going to disappear. And like I said, it disappears way before they have it disappearing, because they got the observer in the wrong point. And that's really all I wanted to say about challenging standard cosmology. It's technically cosmology, but it's, you know, finishes out the series, I guess you could say, and that's why I wanted to do that. Yeah, 2 in 1 day, who'd have thought? And between my first video this morning, or whatever that was, I think it was early afternoon, and now one of my brothers had a heart attack, and so he's going to be okay, but we had a little scare. Mom is still with us. She's 90 years old, if you didn't know, and she's had a stroke, but she's still with us and reasonably happy and comfortable in spite of being in a nursing home. A couple of sisters and brother are there in town watching over her. So, again, I am surprised when anybody shows up, but let's see, comments. blue marker would make the observer hundreds, if not thousands of feet high relative to ball Earth. Yeah, that's the thing. It's a deception. I don't know if, deception implies, and lying implies that the person knows they're doing something wrong, but whether they know that, I can't say. All I'm saying is it's an inaccurate model because it doesn't match real life. It's very fine for mathematics. It's fine for trigonometry and geometry, things like that, but not the real world, because like I said, if you're standing on the Earth, standing upright, you are the tangent point, and you're looking parallel to the tangent of the circle you're supposedly standing on, and things disappear a lot sooner than they should, and according to the model, because you're half the distance to it. Here on the bottom one, we got 7 miles between H0 and H1. And here, the boat is still disappearing, but halfway across, not because there's a horizon point, because you were already there. In other words, I moved this H0 up to here. Okay, and then the 7 miles from that is the H1 is just farther along, and I just made the circle bigger and more less trying to make it cartoonish. I don't know, but not to scale. All I'm doing a proof of concept. Let's see what else we got in the chat here. Yeah, the thing is, I'm using their calculator. Okay, I could only illustrate so much, but their calculator said, like I mentioned, I keyed in I height 6 feet and target distance 7 miles, and they told me that target hidden height was 10.67 feet. Okay, so it's enough to see. You can't do inches. It would be nice to have yards or bigger, but you really stretch it out then, and it's kind of hard to illustrate. But the point is that they put you behind the horizon by 3 miles because they assume the horizon is the curvature. But you can't assume that. You start with the fact that you are the tangent point, and then try to figure out why it disappears in 3 miles. And the obvious answer seems to me perspective. I'm just trying to, as with my other challenging videos, challenging standard cosmology, I'm just trying to present the problem, not necessarily the solution. I'm just saying why I think the curvature calculator is wrong. Okay, and it has nothing to do with perspective or conditions. It's just strictly on its own orthographic basis. It puts you, the observer, at the wrong point. Okay, you can see bird rags miles into the Gulf on a clear day. Yeah, and the thing is, if somebody invokes mirages, that's why I did the mirage video. That's kind of a fallacy of its own when you only use it when it suits you. That's special pleading is that fallacy. And the thing is that you have to be consistent. And again, mathematically, you are the tangent. There's just no way around that. And so if you're going to invoke atmospheric conditions to explain something that shouldn't be there, then why can't we invoke perspective as explaining why something disappears over the horizon? Why is the horizon that far away at that distance? Why is it predictable? It has to do with optics. It has to do with conditions. It does not have to do with some mound of water or earth between you and the target, because you're not back here, you're here. Let's see. Yes, we can see farther than we should. Yes, I'm on top of the ball. We're all on top of the ball, aren't we? That's what a tangent point is. Education system. Yeah. The thing is, again, I'm not going to try to go into the motivation. I could tell you a whole bunch about the educational system back, I don't know, decades ago when I looked into John Dewey and some of these people and the Communist or Humanist Manifesto, which is basically communist, but Humanist Manifesto, which There were some quotes that I have in my head but don't have the references handy, that Dewey and or one of his compatriots in forming or in signing the manifesto said that what can the theistic Sunday schools do meeting once a week to compete with a 5-day program of instruction where the teachers are priests of a new religion? That's the gist of it. And so it is indoctrination from top to bottom, and is designed to make people think what Big Brother wants them to think. But math is math. And here again, if it doesn't have to match reality is the point. Math is by nature circular reasoning, pun intended, but that's how mathematical proofs work. But the thing is, they don't have to match reality. And in this case, I don't think they do, because like I said, we are the tangent point, and that just ruins the whole calculator. Let's see, back to the chat. Yeah, visualizing is the key. I think if you can't visualize something, it's probably bogus. I mean, there are things, emotions and whatnot that you can't quite visualize, but I'm talking about science and math. You have to be able to model things. I mean, people are asking for models. Well, this is a type of model where you work things out mathematically and deal with the real world, which is, I have this observation 3 miles to the horizon, given these the height of the observer and known distance to the horizon from observation. Then we go, okay, this is what I'm seeing. That's all I'm drawing here. And the ground shape is what's in question. Because just to assume their model from their curve calculator, again, not to scale, that's not the point. The point is tangent point. And what the Earth's surface does from there in their model is fall away. Now, the same problem would hold if you had a concave Earth. It would be going up, and this would, you'd have to make an inverse calculator or something for that. But the point is that you have to have reality first and start from there, which is you are a tangent, you look straight out, and things disappear at a certain distance, given your eye height. Or at least that's the horizon. I don't say they completely disappear. They start to disappear then. So I just think it's bad science, bad logic. The math is fine, but the logic is terrible because it doesn't match reality. Let's see, art class, perspective. Yes, exactly. I've seen some amazing drawings. I'm sure you guys have too, where people do street art where it's, depending on where you stand, it looks really awesome. Like there's say some cavern in the ground when it's all just artwork. Well, they have to calculate all those angles and go to a vanishing point and decide on the continually shrinking size of things in order to give them depth. So this is, art and science, but art is more real world than math is, to be honest. Let's see. Yeah, that's the problem. I would like to see how a curve calculator works without U over here. That H0 should be the tangent point. If they can make a curve calculator work and come out with the same horizon, that would be impressive. But I don't know. I don't study all curve calculators. I've just studied this one, and I've heard other people talk about other ones, and they all say pretty much the same thing, and that's where all the math comes from. And the math works for observation because they move you to the wrong point. But if they put you on the right point, the tangent, then things fall apart. Let's see. Yes, anything will vanish if it's far enough away. Kicked out of art class in history. Okay. So, yeah, math has its purposes. It's very useful in engineering. But again, if you wanted, a building with a certain view of the horizon, you have to make it a certain height, and it would be 90 degrees to the surface at whatever point, which is the tangent. And people are going to look straight out, and no matter how tall of a tower they make, you still see the ground come up and the sky come down to a vanishing point. So anyway, I did take math classes back in the day. I didn't take much in art that I wasn't required. I don't know. I doodled all over my books and things, but I didn't take an art class. I think I just didn't want to be graded on it. But it wasn't required, and I was in music anyway, so I didn't have time for that. But I did take math. I had up to college level physics and math. I took trig and calculus in college and physics. But anyway, yeah, vanishing point is a real thing. It's just the way optics work. And if you study the physics of light, you understand lensing, and that's why I did the Mirage video. And before that, the Challenging Standard Cosmology Sun video, because that invokes lensing as a possible explanation for the sun's daily movement and its four motions. So, I guess that's all I got. This is the best I can do to say why I think curve calculators don't work as far as reality goes, because things don't match up, and they try to fudge factor and bypass and account for, invoke optical illusions only when necessary, when their model falls apart, because, like I said, they put you in the wrong point. They say, no, you're not the tangent point. You're way back here, because we start with horizon distance and work our way back. And so, because they assume that the horizon is the curvature, but that's an invalid assumption, because reality doesn't work that way. You are the tangent. You're 90 degrees to the tangent line because you're on the radius and you look straight, and that's just reality. And I think curve calculators don't really deal with that too well. So I have no clue what anybody else is doing video-wise tonight. I didn't even look. I've just been trying to work on this drawing. I changed it like 8 or 10 times, trying to work out what I was trying to express about what was wrong with this calculator. So there you go. And I think I'll stop there. Anybody have a question on the drawings? As I said, I like to make a single point, and the point here is why I think they're making a logical reality error in curve calculators. That's it, I think. I don't see any questions, so thanks again, and we'll see y'all later.